Behind us, we have what we call the NEES UCSD shake table. NEES stands for Network of Earthquake Engine Simulation, and is located at UC San Diego. This is the largest shaking table in the United States. The table can hold 2,000 tons. The structure we have at the back here weighs of the order of 400 tons, so we can still place 5 times more weight than expected.
While testing the structure will calibrate and verify models, it will also serve another purpose. Robert Fleischman gives us an overall view of just what is being tested and why.
What we're testing in the structure is actually 3 different floor systems. That makes it a little bit unique. On the bottom floor, we have double T's that have a very thin topping slab on top with wire mesh. That's a cast-in-place topping slab. On the second floor, we have hollow core with the same cast-in-place topping slab. And on the third floor, we have just precast units, what we call a untopped or pre-topped system. And this is the concept of what we call a total precast system, a total precast solution where the entire structure is made out of precast elements. And so none of these systems right now are specified for an area like California. So really, I mean, what the design profession is doing right now is saying there hasn't been a project like this to show us how precast could be used. So each one of these systems, if we are able to demonstrate their good performance, will represent an advancement in their geographical area where they could be used. And so if we're able to specify a precast diaphragm that works in an untopped fashion, the ability to use a total precast solution in a high seismic area will be a reality.
It is time to start testing. As project partners from across the nation gather, the structure is prepped. Throughout the shake test phase, the seismic records will increase in severity, culminating in an event that might occur once in 2,500 years. The first test, though not as severe, might be as rare, as it is simulating the kind of ground motion that might occur in Knoxville, Tennessee.
5, 4, 3, 2, 1, ready.
The test is a success and the structure performs as expected. Next up is the Seattle Design Basis earthquake, a severe event that might happen once every 475 years.
PCI 3, 270%. 5, 4, 3, 2, 1, running.
A visual comparison of the first 2 tests makes it clear that the seismic hazards faced by Seattle are more severe than those in Knoxville. After these 2 design-based tests, damage was as expected. Robert Fleischman previews his hopes for the upcoming tests.
Next week we'll be testing the Berkeley motions, both a design basis earthquake and a maximum considered earthquake. And if the structure and the floors can survive through those, we'll have successfully demonstrated those systems for those demands.
Due to the severity of the upcoming ground motions, the researchers implement extra safety measures.
Because of the extreme nature of this ground motion, we've added some precautionary measures. We've added 2 restraint towers on either side of the structure. The towers are there just as a precaution to protect the equipment down below, in particular the actuators underneath the table, and they're not touching the structure. They're actually set back 6.5 inches. We don't expect failure, but as a precautionary measure to protect the equipment here on the site, we've implemented safety measures.
Just prior to the day's testing, Jose Restrepo gives a preview of what to expect.
The structure is going to undergo 2 major input ground motions to earthquakes. that simulate conditions in Berkeley. This is the highest seismic region of the country. And we are going to simulate this scenario with a record obtained during the 1989 Loma Prieta earthquake in San Francisco or nearby. And this has very high velocity pulses. In fact, has 5 pulses, 1, 2, 3, 4, 5. So the structure is going to be very severely shaken.
The team is ready to proceed into uncharted territory, the Berkeley design-based test, replicating forces experienced close to the Hayward Fault maybe once in 475 years.
PCI 6, 100%. 5, 4, 3, 2, 1, running.
It is time for the most extreme test ever conducted on such a massive concrete structure. The Berkeley Maximum Considered Earthquake, one we have little chance of experiencing, or so we hope.
PCI 8, 100%. 5, 4, 3, 2, 1, running.
In the end, all settles and the structure stands.
Success. We have to check everything close up, but it looked like it performed really well, so we're excited.
The test phase is complete, with the task of transforming the results into practice ahead. Robert Fleischman comments on how the structure's performance and the test's successes will make that possible.
The testing program at UCSD has successfully demonstrated that our models that we built based on the Lehigh tests have a high level of accuracy. We're really excited about that because what this allows us to do is have confidence in moving forward with parametric studies. We look at all different types of structures all over the country, different configurations, different designs on the computer, and we can say that we have confidence in it because we predicted this test and we ran the test, and the prediction and the response are right on top of each other. I'm also quite hopeful that with the strong team that we have, we can actually truly transform our research into practice and get this into the codes. The result of our work will save lives, will make the construction industry more competitive, will open up markets for precast concrete.
What you're seeing here is the seed crystal of a new dimension in design that's going to propagate over the years and basically overtake the previous ways of doing design work. That's really the value of something like this.